Okay, so we're doing a video on what's called the central limit theorem. This theorem basically says that if you have a population that meets one of two conditions, it's either bell-shaped, so you take a measurement of that population and it comes out already with a central tendency and a bell curve, or the samples that you take of the population are sufficiently large. Usually we consider 30 or more to be sufficiently large. Then you get sample distributions for the mean. So the sample distributions of the mean, or sample distributions for standard deviations that are going to be, sample distributions of means, or sample distributions involving portions of the population. There we go. Sample distributions involving means or sample distributions involving portions of the population. Then these sample distributions themselves will be normal. Okay, so what are we saying here? If you take a bunch of samples of size 30 or more of any population, regardless of how the population is distributed, then the means of those samples, or the proportion of those samples that have a particular characteristic, will be themselves normally distributed. Now, for means of those samples, the mean of the mean is equal to the mean of the population, and the standard deviation of the means is equal to the standard deviation of the population over the square root of the sample size. If I take portions of the population, then the mean of the portion of the population is equal to the portion of the population that has that characteristic, right? And the standard deviation of those portions of the population will be the the portion of the population that has that characteristic times the portion of the population that doesn't have that characteristic over the sample size, and then we take the square root of all of this. Now, all of this we have seen somewhere before, okay? But what we're claiming here is a little bit beyond what we've claimed before, that the original population doesn't need to be bell-shaped if our sample sizes are sufficiently large, and usually any sample size over 30 is sufficiently large enough. Okay, so let's take something like rolling a six-sided die. Die rolls are, generally speaking, uniformly distributed. Okay, so this is definitely not a bell-shaped population. But let's say I take samples of size 100. So I'm going to roll one die 100 times and find the mean. Well, on average, the mean of a population of die rolls should be 3.5, and its standard deviation for that population should be 1.71. Now, that number, the 1.71, is beyond the scope of this course on how to calculate it. So we're just going to kind of let that hang out there as a known fact. Okay, sorry, that's not 1.71. The standard deviation there, no, the standard deviation there is 1.71. That's correct. Okay, so that's beyond the scope of this course, but that is a known fact. Okay. So if I take these samples of 100 and I distribute those samples, then the mean of the means of that sample should also be 3.5, and the standard deviation of the means of those samples should be, well, 1.71 over the square root of n, which is 100, which gives me 0.171. So this gives me the parameters that I need. So just kind of like putting this into the language that we've done before. If I take samples of size 100, ordinary results here should be between 3.5 minus 0.171, which is 3.158, and 3.5 plus 2 times 0.171, which is 3.842. So if I took a sample, 3.842, not 2. So if I took a sample of 100 die rolls and took the mean of those die rolls, if I had something below 3.15 or above 3.85, then I would definitely be skeptical that those were legitimate die rolls, and there might be something odd about that population. So let's take the same situation, rolling a 6-sided die. Now we know from probability that 1/3 of the time I would get a 5 or a 6, right? Because it's 2 out of 6 possibilities, 1/3 of the time I would get that. That's approximately 0.333. Okay, so this means that P, the population of die rolls, right, the percentage of the population of the die rolls that has a result of a 5 or a 6 would be 0.333. So let's say I roll the dice 100 times again. Now, on average, what proportion of those die rolls would be between, or would be a 5 or a 6? Okay, so we know this. We know that on average, the portion of the die rolls should be 333, but that's going to have a standard deviation because some of them are going to have a third, some of them are going to have more. So according to what we have here, that should be that 0.333. Now, the portion that doesn't have that result is 0.667, and my sample size was 100. So if I do that calculation, I'm going to end up with 0.022. So what does this mean? Well, 0.333 plus, well, let's do minus first. Minus 2 times 0.022 comes out as 0.289, and 0.333 plus 2 times 0.022 comes out as 0.377. So of these sets of 100 die rolls, if I were to roll a die 100 times and count the number of 5s and 6s, then between 28.9% of those die rolls and 37.7% of those die rolls should be 5s or 6s. So that gives me the normal target. So this is pretty critical here. This is going to allow us ultimately to draw inferences from samples as to where the population mean and the population proportion is, and that's kind of where we're heading with this as we're moving along.